The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon, everyone. Welcome to my presentation. I'll be talking to you today about our work on modeling the improvement in the capacity of concrete beams and slabs, strengthened with FRP, and utilizing spike anchorage system. So this work was done in collaboration with Dr. Rasheed, who just presented to you the previous presentation. So to start, here's the outline of my presentation. We'll start with the brief background and then mention the objectives of our work. Then present to you the formulation that was utilized to create our model and show you how it was implemented. Present some results with some comparisons with experimental studies and end with the summary and conclusions. So FRP flexural strengthening has become very popular. A lot of research has been conducted in that area. However, in order to push it to the next stage, as we all know, we are limited by in ACI 440 by the debonding strain limit, and ACI 440 currently does not account for anchorage. In order to push the FRP behavior to the next stage, we would need to exceed that limit, and that could be done using anchorage systems. So there is currently a task group in ACI 440 that's working on that, and this research aims to align with the goals of this task group in order to model the behavior of strain in these concrete beams with different types of anchorages. In this case, it's spike anchors. So our model was based on the bond slip model developed by Rasheed and Pervez in 2002. Here I show the differential equation that was developed at that time, and this models the shear interface between the FRP plate and the concrete beam. So this was the developed model, this is the differential equation, this is the solution for the differential equation. What we did is to extend this model to work with and extend it to model anchorage in concrete beams, which is on the next slide. So this is the case that we are working with. We have our beam strengthened with an FRP plate that has a length of LP. This is half of the beam, the rest is symmetric. So the length of the beam is LP, the length of the plate is LP. And here we have two main regions. The region between the anchors is fully bonded, and for that we use the shear modulus of G1. We have the second region, which is the unbonded region, and that utilizes the shear modulus of G2. So we utilized the solution of that equation and applied it to the different regions here. The shear stress in the bonded region is according to this equation, and then we have the shear stress in the unbonded region before the load, and then after the load, the beam is loaded under 4-point bending here. And of course, the shear stress in the area before the first anchor at the tip of the plate. So in order to obtain the total force in the interface, we integrate the shear stress along over the span of the FRP plate. And it's worth noting that in order to simplify our model, we just included in the model the first and the last active anchor. So we might have more anchors here in this bonded region. However, the model accounts for only 2 anchors at a time. And then we expect that in between the same behavior occurs since it's still fully bonded. So in order to solve so we had about 8 constants in our solution earlier. And in order to solve that, we need to apply boundary conditions to find out these constants. And these are the boundary conditions used. To summarize, they're mostly basically the fact that the shear strain at an anchor is 0, and also to account for continuity between before and after the anchor with different within the bonded and the unbonded regions. So applying these boundary conditions, we were able to obtain these matrices to solve for the constants here from A to H. several of these matrices and equations, and if we apply them, we're able to calculate the constants and then use them in our model. So now that we have our model, we moved ahead to implement it. So we implemented it in a spreadsheet where the inputs are the geometric and material parameters of the test specimen to be investigated. And here we have our matrices. We invert the matrices in order to solve for the constants. The analysis is done by applying the load incrementally beyond debonding. So assuming that we are now at the debonding stage at the last anchor, we apply more load there, a load step, and we perform our analysis. We calculate the force in the interface from that, and then calculate the moment in the section. Compare that with the applied moment. We see if we converge or not. If we converge at that step, we move ahead. If not, we reiterate until we converge. I should note that one of the parameters used is the location of the last anchor. So at first debonding at the last anchor, we utilize the maximum spacing between the anchors. And if we converge, we say that debonding occurred at that anchor. And now in the next step, when we add more load, we'll actually change this parameter, which is LAN, right here. And the parameter is now goes down to the distance between the plate and the next intact anchor. So we keep repeating this process for each anchor until we reach the ultimate load. So we compared the results of our model with an experimental study conducted by Smith et al. In year 2011. It was published. In this study, some slabs were tested. Here we show the geometric properties of these slabs, and there were so the span was approximately 2.4 meters. The plate was 2.2 meters long, and it was tested under 4-point bending, as shown. So we're going to compare the results with two slabs that were tested, which were S7 and S8. The difference between the two slabs is shown in the anchorage configuration. So S7 had one type of spike anchors, uniformly distributed within the shear span, while S8 had two different types of spike anchors as shown. Now, in this table, I show the ultimate load predicted by our model versus that of the experiment. You can see that for slab 7, we predicted 51.44 kilonewtons compared with 51.48 kilonewtons obtained from the experiment. For slab S8, we predicted 54.33 kilonewtons compared with 54.3 kilonewtons. So we are very close to the experimental results here. Next, I'm just showing what the ultimate load that we predicted versus the debonding, the load at debonding, which would be the limit state if we didn't have anchorage, to show the effect of anchorage in this case. And we can see that for slab 7, the strength increased from 43.54 kilonewtons to 51.44 kilonewtons, and that's about approximately 18% increase. While for slab 8, the strength increased from 43.56 to 54.33 kilonewtons, and this is 25% increase. So this shows the effect of spike anchorage and how it improves the behavior. Now for slab S8, actually in that paper, the debonding crack propagation was provided. So we were able to actually compare, as I said previously in the implementation part, we apply load step until the debonding crack or debonding occurs at an anchor, and then we increase the load and go on until all anchors fail. So we were able to compare the loads that we had at each step with the loads obtained from the experiment. And so slab 8 had 6 anchors on each side, starting with anchor 6. In the experiment, it failed at 45.4, or the cracking reached anchor 6 at 45.4 kilonewtons, while we predict 45.9 kilonewtons, which is the difference of about 1.1%. Moving on, for anchor 5, the experimental load was 49.2 versus 47.56 from the experiment, and so on until we get to the last anchor, anchor 2, at which we had the load experimentally be 54.3 versus 54.33 kilonewtons from the model. So we obtained some good agreements with these specimens. So to summarize, in this work, a model was developed in order to quantify the improvement in the section capacity through the use of spike anchors. And this proposed model was then implemented and used to compare with few experiments. And the analysis results and our results show that we obtained good agreement with these results. So this concludes my presentation. I'd like to answer any of your questions.
Great, thank you very much for that. Questions? I'll ask the first
I have
one.
a question. In that last slide, were you showing various anchors failing?
Yes.
So you're saying when you got to the load fail anchor 2, 3, 4, 5, and 6 are already failed?
Yes. So basically the load increases. As you can see, the load is going up. So yeah, basically we had debonding reach. So when debonding reached anchor 2, we had failure at the anchors before.
So does that mean if you just installed anchor 2 and didn't do 3, 4, 5, and 6, you would have gotten 54.3 capacity?
That wouldn't be the case because what we are doing is an incremental analysis. So the results would have been very different if we immediately started applying the load at the location 2 rather than starting with. So what we did is incremental. The results wouldn't come out to be the same now. We expect it to be a lower load.
And I also have a general question.
Sure.
You make this FRP fireproof by adding fireproofing to it?
So yeah, so as the similar question was asked in the previous presentation, the code takes care of that by utilizing a load lower that the beam without the FRP needs to take a lower load combination. So that's how it's accounted for. But there are some fire retardants that can be used, and they are used in the field in order to increase the resistance of the fire resistance of the FRP. Sorry?
I was talking to a contractor who says he does a lot of this work, and I said, well, what about the concerns about fire? And he said, well, we just put fireproofing.
Exactly, yeah. So there are some, it depends on the county and where you work. There are codes, and some counties refuse to accept FRP strengthening, we are very strict, but some who are progressive actually look at the test results and look at the different techniques that are used to retard the fire effect, and they accept that. Thank you.
Can I ask a question?
Sure.
Thanks. Oh, just on this plot, it's a really good correlation. So how did you determine where the debonding crack was in relation to the anchor?
Sorry, could you repeat that?
How did you determine sort of how the debonding crack moved along in relation to the anchors? Based on the paper?
Yeah, exactly. So I believe in the paper it was mentioned that it was done visually. So they recorded where the loads were at where the crack was visually observed to be. And then we just, in our analysis, we just placed the anchor at that location in our analysis, and then we assumed that the crack was there in our analysis, and we obtained the load.
Yeah, the cracks were measured visually.
Yep.
Because of my students doing the work. So there may well be some variation, but what you've done there is really good work. You've predicted the response really well. So
Thank you.
great work.
Good question.
Yes.
Differential equation. How did you take into account in the differential equation the effect of the anchor?
The anchor. So it was based on the boundary conditions. If I go back. So the boundary conditions applied, specifically the ones where we have the shear strain at the anchor location set to 0. That's what takes care of the anchorage in the model. Thank you.
If there's no more questions, we'll call this presentation to a close. Thank you very much.
Thank you.